you. Thank you. I want to thank the organizers for inviting me and for giving me the opportunity to speak here. The title I'm going to talk about is the K-theoretic and the motivic hyperKähler resolution conjecture. And it is a series of joint work with Zhiyu Tian in Grenoble and Charles Vial in Bielefeld. So I guess the title of the talk, I don't have to justify first two words, giving the name of the program, and I will start with the word hyperKähler resolution. Okay, so I will work over complex numbers in this talk for simplicity, but some results are generalizable to other contexts, at least in the case of characteristic zero and algebraic closed base field. So I start with the definition of a notion a little bit more general than the hyperKähler resolution. It's called Krapent resolution. So let X be a normal algebraic variety. I will assume that it has at worst Gorenstein singularity. So Gorenstein means it's Cohen-Macaulay, and the dualizing sheaf is actually a line bundle, or you can say that the canonical Weil divisor is a Cartier divisor. So this condition will always be satisfied in this talk. And a resolution of singularity, I will say just a resolution, y to x, and call this pi. So a resolution for me is always a projective birational morphism. Such that, birational morphism. And is called Krapent if there is no discrepancy, namely the pullback of the canonical bundle, which is well defined due to the Gorenstein condition, is exactly the canonical bundle of Y. So this is some minimality condition on the resolution of singularities. So you can think of if one blows up further, say Z to Y, for example, along some smooth center of Y, then the usual blow-up formula tells that the canonical bundle of Z is the pullback of the canonical bundle of Y plus some codimension minus one codimension of the center that we blow up, minus one plus times the exceptional divisor. So this part is classically called the discrepancy of this birational morphism. And the absence of the discrepancy is exactly the minimality of the resolution, namely that this further blow-up won't be necessary if you just want to get some smooth model, birational model. So this is just a historical remark for this terminology. So let me give some very easy examples of Krapent resolutions. So some easy examples. The examples of Krapent resolutions. So let me stick to dimension 2 case. In dimension 2 cases, it's called ADE singularities. There are a lot of other names, for example, Duval singularity or canonical singularities. And the simplest example, simplest case is the following. Say if we have an involution of C2 which maps the coordinate xy to minus x minus y. Then of course it's generically free, but at the origin we have a fixed point, and that's exactly where the problem of the singularity appeared. So the quotient is very easy to compute. So this is of course spectrum of C, xy, and R invariant. Yeah, and this ring is very easy to see that. So it's x squared, y squared, and xy. Yeah. And if I call this variable u, this variable v, this variable w, then this is spectrum of C, U, V, W, satisfying the usual equation that U times V is the square of W. Of course, this is classically known as the quadratic, the projective cone over the conic in P2, smooth conic in P2, and the only singularity of this space is at this vertex of this cone, and if we blow up this singular point, we get an exceptional curve, which is P1, whose self-intersection is -2, and it corresponds to the so-called A1 singularity. And the Dinking diagram is just a point, and we can put the self-intersection number -2 here. So in general, it's just some singularities, such surface singularities, such that the exceptional set is a bunch of -2, a bunch of smooth rational curves with self-intersection -2, and the configuration is fixed by the Dinking diagram type ADE. So this is just give you some idea of what Krappan resolution is. And now a special case of Krappan resolution is the following notion of hyperKähler resolution that I'm interested in. So definition. Before defining hyperKähler resolution, let me define what is a hyperKähler variety. So let's say M, a smooth projective variety over complex numbers. Let me assume that this variety is simply connected. Then holomorphic symplectic form is an element, is an algebraic two form. So it's a holomorphic form. It's not of type 1, 1. So it's not the symplectic Kähler form that we are talking about usually. So it's really some algebraic information. Such that sigma is, such that sigma is non-degenerate at any point x of m, which means that sigma to the power of dimension m over 2 is nowhere 0, is nowhere vanishing. Okay? So in particular, m is even dimensional and m has trivial canonical bundle. So the importance of such smooth projective variety is somehow justified by the celebrated theorem of Bogomolov and Bourvil, saying that if we have a smooth projective variety whose first Chern class is trivial, is 0, then up to going to a finite A-Dao cover, the cover can be write as a product of an abelian variety times a strict Calabi-Yau variety times a such holomorphic symplectic variety. So it's one of the three basic building blocks of a variety with trivial canonical bundle. And just to give you some quick examples. So the problem with holomorphic symplectic varieties is that there are relatively few examples comparing to the Calabi-Yau case. So here are some standard examples. So for K3 surface, and I guess in this, simply connected, so no. K3 surface, and for as a K3 surface, we can consider the Hilbert scheme of endpoints on S by the theorem of Fugate. This is always a smooth projective variety, and moreover, since S is a K3 surface, this carries a holomorphic symplectic form coming from K3 surface. Maybe I should recall that a K3 surface for me is a smooth projective variety of dimension 2, which is simply connected and whose canonical bundle is trivial. So in particular, have a symplectic holomorphic 2 form, which provides in this case. And if A is an abelian surface, then we have the the generalized Kummer variety, which is just the fiber of the same construction, but with n plus 1. So this is the Hilbert scheme of n plus 1 points on this surface A, and we can always count the multiplicities of its supports, goes to the symmetrical product. Then we use the group structure on this surface. We get to an element of A, and a fiber of this, or every fibers are isomorphic. So any fiber of it is called generalized Kummer varieties. The name comes from the fact that if we take n equals to 1, this is the classical Kummer surface associated to this abelian surface. So this is a generalization. So this is called generalized Kummers. Okay, and there are many very interesting examples in classical geometry. So any moduli space of sheaves on K3, for example, or a Fano variety of lines on cubic fourfolds, etc. I don't want to say a lot more about that. So, and moreover, any deformation of such varieties are also holomorphic symplectic. Now, as I'm talking about HyperKähler resolution, I have to deal with singular holomorphic symplectic varieties. So for me, the HyperKähler word is just a synonym of this holomorphic symplectic. It's not really, there are some subtle differences, but I don't want to insist in this talk. So let's stick with holomorphic symplectic terminology. So this is the first point of the definition. Second point of definition is a singular holomorphic symplectic variety. So if X is a normal variety, projective normal, say. Projective is not very necessary. Normal variety is called holomorphic symplectic if the smooth part carries a holomorphic symplectic form in the sense above. So if the F regular, there is an element in H0 of the smooth part, which is symplectic, and plus the condition that sigma extends to just a holomorphic 2 form, not necessarily symplectic, holomorphic 2 form. So if you want algebraic 2 form on a resolution or on any resolution, this is equivalent. So, this notion is independent of the choice of the resolution due to the, anytime you have 2 resolutions, you have the third one to cover them. Actually, we have a more intrinsic description due to Namikawa of this singular holomorphic symplectic variety. Namely, a normal variety is a holomorphic symplectic if it carries, the smooth part carries a holomorphic symplectic 2 form, and the singularity of X is not too bad in the sense that it's Gorenstein and a rational singularity. So it's really some intrinsic thing. Some examples also for singular ones. So the only example that I'm going to use for this talk is the quotient of a holomorphic symplectic variety by a finite group action by symplectic automorphisms. So M, holomorphic symplectic, and G, X on M, it's a finite group action by preserving the symplectic form, or one symplectic form. This is not very important. Then M over G, this singular variety is an example of such singular holomorphic symplectic varieties. Of course, there are some interesting examples in the literature. For example, some singular moduli space of sheaves, etc. Singular moduli of sheaves on K3. Or in representation theory, people are very interested in the nilpotent cone of some Lie algebra, semi-simple Lie algebra, nilpotent cone, etc. Okay. Now I can talk about a special case of the Krapner resolution, namely the HyperKähler resolution. But as I said, I will stick to the terminology symplectic. But the conjecture gets its name, so. Okay, symplectic resolution. Oh, I should switch board. Okay, symplectic resolution. So let X be a singular, so not necessarily smooth, singular holomorphic symplectic variety, in the sense on the left. A resolution y to x is called a symplectic resolution if the or one symplectic form on X regular extends to a symplectic form, holomorphic symplectic form on Y. So the difference, the only difference between this definition and this symplectic resolution is that we require that the extension of this holomorphic symplectic form is not only a holomorphic 2 form, but also symplectic. And we also have an intrinsic definition of this condition. Actually, this is equivalent to the requirement that the resolution is crebant. So yeah, you can say that I'm defining the same thing twice. So it's equivalent to the crebant. Okay, and I will just put one example, and I will come up with all other examples later when I state the main theorem. So I just make one example. So if S is a K3 surface, then we can look at the symmetric product of this surface, which is just the quotient of the nth product of a surface, quotient by this natural action by permutations of the symmetric group. This is a singular variety. And the aforementioned Hilbert scheme is one famous HyperKähler holomorphic symplectic resolution of this singular variety. Is a symplectic resolution. Okay? So this fits into the example here that Sn is naturally a symplectic variety, and the permutation will preserve the symplectic form. So the quotient is a singular symplectic one. This, as I said, is a smooth symplectic one. So this is a perfect example for the definitions. Now, the slogan of this talk. Well, personally, I'm interested in the study of algebraic cycles, or more generally, the motives of holomorphic symplectic varieties. And the slogan of this project is that one can study the Chow ring, I mean, more than just the geometry of holomorphic symplectic varieties via the hidden orbifoldal structure on their singular models. Okay, this is the slogan. So in this example, I'm saying that to study the geometry of the Hilbert scheme of K3 surface, we should develop some geometry of the orbifold structure on this symmetric product, which is actually very natural because it's written as a quotient of a variety, smooth variety. by a finite group. Yeah. Now, the second section is the last word in the title, the conjecture. Okay, the conjecture. So the setting for the conjecture is the following. So this conjecture, I will talk about cohomological versions. The setup is the following. So fix a complex orbifold. So in the algebraic language, we could say that it's smooth, usually proper in my talk, the Ligging-Mumford stack, okay, over the complex numbers. Of course, we should assume that the generic stabilizer is trivial. Okay? That's not very important. Now, the Roman X is the underlying singular variety. So the coarse moduli space. And we should assume, as always, that assume X is Gorenstein. Technical condition. Now, because this orbifold is naturally associated to this, this underlying singular variety, we could say that X is one of the best models, best smooth models of these underlying singular varieties. Now, if moreover, y to x is a Krapin resolution, I said before that a Krapin resolution is also considered as a minimal, a best smooth model. Is also a best smooth model of the singular variety X. Now we have the competition. We have two smooth models of the same singular guy. Now some considerations from physics, theoretic physics, especially string theory, tells that actually y and the orbifold X should give same cohomology theory in a very complicated sense. So, string theory says that once we have such kind of Krapin situation, the quantum cohomology of this orbifold, usually with complex coefficient, should be isomorphic in some sense to the quantum cohomology of y. So this is just a prediction. There is no precise mathematical reason behind it. So here the isomorphic is, should be taken in the following sense. So usually in quantum cohomology, there is a quantum parameter, usually called Q or tau or U, depending on the situation. So this isomorphism means that they are isomorphic up to change of variables plus some analytic continuation. So it's in a really vague, for me, it's in a really vague and really vague sense. But our situation is simpler. We can take classical limit. So the classical limit gives us that if we take the quantum parameter here to 0, and here the quantum parameter goes to -1, they are taken these values for some good reasons, but that I don't want to explain here. We get the so-called orbifold cohomology of the orbifold X that Gonzalo talked a little bit about yesterday. Yeah? And here we get so-called quantum corrected cohomology of Y. And now we have, we really expect some isomorphism of complex algebras. Just to get some feeling of these two algebras, let me talk about their underlying vector space and their products, which is not that complicated to understand. To define. Oh, I forgot to say that this orbifold cohomology ring is constructed by Chen and Ran in the 80s, 90s maybe. So just some to give some flavor. So this orbifold cohomology of this orbifold as vector space, graded vector space, is just the cohomology of the underlying singular space of the inertial stack. This is a vector space. But together with the product given by some moduli space of curves, stable morphisms from orbifold curves actually to this X to some beta that I don't want to enter detail. But this moduli space comes equipped with the evaluation map. So an element in this moduli space is just a morphism from a curve, but with some orbifold structure to this orbifold, and with 3 marked points. Then we can read the image of these 3 marked points. We get evaluation map into, usually should go to the cube of this variety, but in the case of orbifold, it actually naturally ends to the inertial stack of this orbifold. That's why we get a product on this cohomology. See, we always, by Gromov-Witten theory, we always have a virtual fundamental cycle, which is just some cycle in this moduli space. We push forward, we get a cycle on the cube of some variety. And a cycle on the cube of a variety can be viewed as a correspondence from Ix times Ix to Ix, which gives a product on the cohomology. That I will, this point I will explain later in more detail and in a more down-to-earth fashion for the global quotient. And on the other hand, the quantum corrected cohomology of a variety as a vector space, it does not change anything. It's just the usual cohomology of Y. But the cup product is changed by some quantum correction with the cup product modified by the so-called quantum corrections controlled by the same kind of moduli space, this time in Y. And here, beta is also a curve class bit, but this is contracted. So I can say contracted by this resolution of singularities. This is pi. Okay, and it also has the evaluation map to Y cube. And as usual, a cycle on Y cube will give up some amorphism from the cohomology of a Y times Y to the cohomology of a Y. This is exactly the modification, the quantum corrections on the cup products. So here comes the conjecture. This conjecture is due to Yongbing Ruan. Conjecture runs cohomological homological cramped resolution conjecture. Usually people write as CCRC. Okay? So it says in the above setting, namely an orbifold and with a cramped resolution of the underlying singular variety, then the orbifold cohomology constructed by himself is isomorphic as C algebras, isomorphic to the quantum corrected cohomology of Y. So here all cohomology theories are taken with complex coefficients for some reason. This is a conjecture. Now our story gets even simpler. If moreover, Y is holomorphic symplectic. Holomorphic symplectic. Then we know that for a holomorphic symplectic variety, all Gromov-Witten theory vanish. Because every curve class, we can always deform it to some non-Hodge type class. So every quantum correction will vanish. So we get really a down-to-earth statement. This is his cohomological HyperKähler resolution conjecture. Usually one writes as CHRC. Okay? It says the following, X to the underlying orbifold, and if X is a symplectic holomorphic, singular holomorphic symplectic variety, singular holomorphic symplectic, and the pi is a symplectic resolution, which says in particular that Y is a holomorphic symplectic. So there is no quantum correction. Then we get from the more general conjecture the following conjecture. So the orbifold cohomology ring of the orbifold is isomorphic to the usual cohomology ring, the Betti cohomology ring of Y. So this explains our slogan that to study the cohomology, for example, the geometry of Y, we can study the orbifold cohomology of X, which is actually not necessarily more complicated on the right than the right-hand side. And in many cases, it's even simpler. That's our general principle. Now the question is that, do we get a more geometric explanation of this isomorphism? Namely, can we lift this kind of isomorphism for motives, for Chow, for K-theory? I don't understand, sorry? So you mean this orbifold? So this orbifold has no generic stabilizers. In other words, if you are looking at the global quotients, then this group is acting faithfully. Yes. So yes, the answer is. So now our precise conjecture, precise formulation of our conjecture. So to formulate the conjecture, let me define or recall the left-hand side, which may be a little bit mysterious for you. So let me define it properly. What is the underlying space and what is the product? So let me restrict myself to this global quotient case. So M is a smooth projective variety, and G is a finite group acting faithfully. And we assume that this action satisfies the Gorenstein condition. This is just some technical condition, Gorenstein condition. We assume that for any G and X, such that X is a fixed point of G, then G lives in the G gives some automorphism of tangent space, and we assume that the determinant of G is 1, so it's the Gorenstein quotient. So in this setting, we are going to define, so let me say orbifold cohomology of this quotient orbifold, okay, as exactly the same formula that Gonzalo used yesterday. This is the direct sum over G, and we look at the cohomology of the fixed point of G, but with some shift. It's twice the age of G, and with a non-trivial orbifold product, then we take the G invariant. Okay, let me explain all these ingredients. So step 1, what is the age? So for the age function, this is very classical due to Miles rate, I believe. So if we fix G, and for age G is the locally constant function, defined in the following way. So we take any irreducible, connected component, the number, the value of the function on this component is, so how to define this now? I first restrict the tangent bundle of M to Z. Of course, I get a natural action of G on this vector bundle, because Z is fixed by the element small g. So we have a natural action of G. And I can decompose this into eigen subbundles. So this is the decomposition. Let me say J is to 0 to R minus 1, Wj. So where R is the order of G, and the Wj is with the eigenvalue, eigen subbundle with eigenvalue e to, you can guess, to e to the 2 pi I over R times G, J. So we decompose the restriction of the tangent bundle to the fixed locus into eigen subbundles, and the age function is just some weighted sum of the ranks of these eigenbundles. J is equal to 0, R minus 1, and the weights are J over R of the rank of Wj. This is the age function. And as you can see, thanks to the Gorenstein condition, the determinant of this action should be 1. So all the sum must be all the sum must be an integer, because the exponential of this thing should be 1. So therefore, the sum should be a multiple of 2 pi I, and this is an integer. So this is an integer due to the Gorenstein condition. Okay. Step 2. Step 2, let me define this orbifold product star there. So to define this, let me call SG, this still using the same notation. This is the virtual bundle that WG. So the decomposition of the restriction of the tangent bundle is the direct sum of Wj, and this bundle SG is some virtual bundle on this fixed locus. So the class of this eigen subbundles with some weights. So it's just some virtual bundle. I can put a rational number here. And finally, another virtual bundle, Fg, on it's by definition it's just mgh, sh, mgh plus gh inverse minus the normal bundle of mg over m. Of course, this is also an element in the Grothendieck group of mgh rational. So where mgh is just the intersection with reduced structure of these two fixed loci. And a remark is that this virtual vector bundle is actually the class of a genuine vector bundle called the obstruction bundle. This is obstruction bundle. Obstruction. This is proved by Jarvis, Kaufman, Kimura. All this presentation is of the orbifold product is following the paper of Jarvis, Kaufman, and Kimura. And they prove that this actually comes from a genuine vector bundle. Now the product is defined by in the following way. So the quantum product from, say, cohomology of mg 10 times cohomology of mh, and the quantum product will respect the G grading. So it will be a class for the fixed locus of G times H. And the formula is very simple, yet highly non-trivial. For a class in Mg, a class in Mh, we are looking at 3 natural inclusions. Maybe I should lift the board. We have 3 natural inclusions. So the first thing is to restrict alpha and beta in the smallest fixed locus and do cut product. I will write cut product as intersection product just to be coherent, consistent with the later presentation. And times the highest Chen class, the top Chen class of this obstruction bundle. This is the non-trivial part. And then I do this inclusion with respect to this last inclusion, the push forward. So I repeat. So the quantum product is given by first restrict 2 elements from Mg, fixed locus of G, and an element on cohomological class on the fixed locus of H. We restrict to this smallest fixed locus, and we do intersection product, and then we cut product with the top Chen class of this obstruction bundle. Then we push forward to this MGH. This is the orbifold product. And of course, the highly non-trivial fact is that this product is associative. It's a miracle. Now I think I can finally define the orbifold product. Orbifold cohomology. By fixing the 1, 2, 3, by explaining the G action in the end. So the G action, this is the easy part. So for any G, in G, of course, G will induce a natural isomorphism from the fixed locus of H to the fixed locus, I guess, Hg minus 1. Yeah? So this is an isomorphism for any G and any H. And of course, this will induce an isomorphism on the cohomology. And the H function is actually invariant on conjugation. So this won't affect the H shifting. And we can remark that, we can check that the orbifold product is compatible with the cohomological grading, with the G grading, with the H shifting, and with the G action. Everything is compatible. And finally, we get to define the orbifold cohomology ring of this orbifold, quotient orbifold, as this, I will repeat, as this big direct sum with this product associate. Then we take the G invariance, which is of course a subring. So this is just in general an associative ring. But it turns out after we take the G invariant subring, it becomes a commutative ring. And it turns out that this construction does not depend on the pair of the action G and M, but only on the orbifold, the quotient orbifold of M over G. Okay? So if you find another presentation of the quotient, we get the same cohomological algebra. So it's really some intrinsic invariant, some intrinsic algebraic invariant of this orbifold. Okay? Now, let me use all these blackboards to define other invariants that I'm going to use, namely the orbifold Chow ring and the orbifold Chow motive. So the only thing to change is that I put C here to Chow ring. And basically nothing changed. So Chow ring. And of course, I have to adapt this formula for Chow rings, but it's already Chow ring friendly. We have a restriction, we have product, we have Chen class, we have push forward. Now for Chow motive, what did I do? If you have some working experience with motives, once we understand the Chow formulation, it's not so difficult to get to the motive setting. So for me, the weird H is for the Chow motive. And here, a morphism from two motives is given by correspondence. And of course, we are giving this product as a precise correspondence. So given by the correspondence, the correspondence delta push forward of the top Chen class, where delta it is just another way to say restriction and push forward of mg times h into mg times h times mgh, which is the small diagonal embedding. Yeah. And here, the Chow orbifold Chow motive of the quotient stack is the direct sum of the motive of mg. Now the H, of course, when we're talking about Chow group, we should forget this too. Yeah. And for Chow motive, the H shifting becomes a Tate twist. So it's Hg. And the product is just this one. Yeah, this is it's the same thing, product. And we have, because the category of Chow motives is idempotent complete, we can always take the G invariant sub algebra object. Yeah? So this defines everything, I guess, but the title of this program is called K-theory. I have not yet talked about K-theory. So let me also define K-theory of the orbifold. It defines in the same fashion but as in K-theory, there is no grading. I mean K0 theory, I mean the Grothendieck group. K-theory. So this is well defined, but I have not said what is the orbifold product. Well, nothing something will change, but only here we will replace, when talking about K-theory, we replace the top Chern class by this lambda minus 1. Yeah? Lambda minus 1, and by technical reason, it actually turns out to be the lambda minus 1 of the dual of the obstruction bundle. Of course, this product is understood as tensor products, and the push forward as push forwards of K-theory. Okay, so everything is defined in the orbifold setting. Yes. Okay. Now, the main conjecture. I can keep this. The main conjecture that we want to call this motivic HyperKähler resolution conjecture. So in the above set, in the setting that M is a holomorphic, symplectic, and G is a finite group acting faithfully. Finite group acting faithfully, such that and preserving symplectic form. Now we get this if y to this is a symplectic resolution, then now the strongest conclusion would be the motive of the quotient stack, the orbifold Chow motive of the quotient stack is isomorphic to the motive of y. But be careful, this is an isomorphism of algebra objects, or just algebras, in the category of Chow motives. Algebra. In the category of Chow motives. So on the left-hand side, I just explained what is the algebraic structure. But on the right-hand side, what is the algebraic structure on this motive of a smooth projective variety? Well, this is a standard. Each time we have a smooth projective variety, we can look at, so an algebra is just a morphism of motive from, this is an algebra, and this is the multiplication. And a morphism from, this is hy2, and a morphism from the motive of y squared to the motive of y is given by a correspondence in the product of y squared times y. So this is given by the small diagonal. If you if you think of the cup product, this is exactly given by the small diagonal in the cube of a variety that gives you the product structure. Yes, a cup product of two cohomology class is just to pull back from two projections, and a cup with the class of the small diagonal, then push forward. So here is the same. And of course, this strongest conjecture would imply some concrete things. For example, for Chow rings. So orbifold Chow ring would isomorphic as algebras, C algebras to this Chow ring of Y. And also, by using the orbifold Chern character, we recover the conjecture of Jarvis, Kaufman, and Kimura on orbifold K-theory should be isomorphic still as C algebras of the usual K-theory of Y. And of course, all these topological invariants like orbifold cohomology or orbifold topological K-theory would also be isomorphic. Because we have a motive, we can apply any realization we want to get this.
So is this a
Sorry?
Is it C algebra?
As complex, yeah, as C algebras. So this is no longer, this is not only an isomorphism of vector spaces, they also preserve the multiplication structure. C algebras, everything is, so yeah, this is a general, yeah, I forgot to say that in general I will use complex coefficients. Actually, the Q coefficient adjoining the square root of -1 would be sufficient. But I mean,
Is there some problem with the Chern class? Why is this not defined directionally?
yes, if you are willing to change the definition of the orbifold product by something called discrete torsion in theoretical physics, in our case, it's just a very concrete sign change. You change a sign in the product, it will be okay for rational coefficients. So in principle, you can understand it as rational coefficient, but I don't want to state anything wrong. Now, the evidence. I will state these evidence through some examples. The first one is surface case. So if S is a K3 surface or abelian surface, G acts on S, a finite group as usual, and we take the minimal resolution. Then then the conjecture holds. MHRC holds. So some remark. If we are only considering the cohomological version, which is CHRC, this is actually classically known as Mackay correspondence. But more than that, Mackay correspondence is just an isomorphism of vector spaces. I mean, you get a bijection from the isomorphism classes of representations on one hand, and the classes of exceptional curves on the other hand, irreducible components of exceptional curves on the other hand. But this is stronger. We are here, the cohomological version says that there is also a ring isomorphism. But this is, I believe, is also classically known. And the motivic version is not very different from the cohomological version, and we think it is, it's never written down, but we are gonna write it, and it should be known to experts.
The G here
Is any, symplectic automorphism group. Yeah. And 2 is the local case. This does not fit into our framework very well, but I'm gonna say it because it's also something highly non-trivial. So if we have a symplectic vector space, symplectic C vector space, and G is the symplectic, is some, finite subgroup of the symplectic automorphism of this vector space. If, say, Y is a symplectic resolution of this guy, symplectic resolution, then the analog of motivic hyperKähler, the analog of the cohomological hyperKähler resolution conjecture holds. This is a very difficult work of Ginsburg and Kaledin. So I should say that this work uses essentially the cohomological methods. So their interpretation of the orbit for the cohomology is some kind of Poisson cohomology or pericyclic cohomology. So this method, as far as I know, cannot be improved into any motivic level or K-theoretic level. So it would be very interesting to investigate the local case for our conjecture. Now, some positive, other positive cases that we can prove is concerns the examples that I talked about earlier for symplectic varieties. 3. So let S be a K3 surface. Then we take n just any natural number, K3 or abelian surface. Then for any number, we look at the nth power of this surface, and we look at the natural action by the symmetric group. And of course, the quotient will be the symmetric product with which is a singular symplectic, homomorphic symplectic variety. And there is a preferred resolution of singularities given by the Hilbert schemes. So here, this is Y. This is a symplectic resolution, and the motivic HyperKähler resolution conjecture holds. Also, some remarks in order. So the cohomological version for abelian surfaces and for K3 surfaces are known by the work of Fandaki-Goche and independently Uraib, I don't know if I pronounced it correctly, based on the work of Lenz-Zorger. This is a very difficult work on the computation of a cohomology ring of this Hilbert scheme. And our method does not give a new proof of that. Actually, we use their cohomological information to upgrade to the level of motifs. And actually, we need more. We need not only their computation of cohomological the cup products on the cohomology of Hilbert scheme, but also we need the cohomological cramped resolution conjecture that I stated in the beginning for every surfaces. For every simply connected surfaces. So not only for K3, but for any for other surfaces. So it's a really complicated method that I think don't have time to talk about. I'm sorry for that. And finally, so this is theorem that I joined with Tian, and the fourth is I joined with Tian and Vial is when A is an abelian surface. Then we look at M to be A M plus, the kernel, how to say? So we look at A to the power of M plus 1. This has a summation map to A. And we look at the kernel. Of course, this is non-canonical isomorphic to A to the power of N. But it comes equipped with a natural action of Sn plus 1. Because we can permute these n plus 1 factors. And the Kummer, generalized Kummer variety, is a symplectic resolution of this guy. Is a symplectic resolution of this guy. And the motivic HyperKähler resolution conjecture holds in this case. And also one remark. In this case, even the cohomological version is not known. So the cohomological version is a byproduct of our proof. Yeah. And that's the evidence that I can provide. When should I stop? Now?
Well, you already 4 minutes.
Oh yeah, so I'm sorry. So that's also I'll stop here. I'm sorry that I cannot talk about proofs or applications. Yes?
Okay, go
Sorry? Oh yeah, G. This is classical. Every time you have a Chow motive, say M, in the category of a Chow motive, with an action, of course, the G. Then the G invariance is just the how to say the image of the projector P from M to M. This is idempotent complete. So every projector has an image where P is the sum of G. Yeah, G is a morphism. So sorry, 1 over G. Oh, I should say yeah with rational coefficients. Otherwise, and moreover, if M is an algebra object in this category, then this the invariance is also an algebra object. That's very easy to check. It's just like usual algebras. No more complications. Please?
My question is, the conjecture says something about the map.
Of the?
Map.
Oh, yes. Actually, yes, I have some proposal for this map, which map should induce this isomorphism. And in every example that we can prove, there is a very geometric example. Let me say just one word. In the case of Hilbert scheme of K3 surfaces, this resolution, then what is this? What kind of correspondence will induce this isomorphism? So this is given by the following. So we have here, we have nth time to the quotient, and here is the resolution. We can form the incidence variety, which is the reduce the fiber product of this square. So we get the so-called isospectral Hilbert scheme. But anyway, this is just terminology. So a point in here is just a length n subscheme on the surface plus n points such that the support of the scheme is exactly the sum of these points. So this is very easy to understand. And now for any G, this is just some partial diagonal in the product. And it actually Gx also on UG, that's why this incidence variety is also called U superscript G. And this UG for each G will be a correspondence from the Hilbert scheme to this fixed locus. And as you can see, the definition here is given by the direct sum of the fixed locus. And this, with appropriate coefficients, will give you a multiplicative isomorphism. And if you don't have a question, I have a question. I'm sorry. So if as Gonzalo explained yesterday, the derived category allows us to recover this orbifold K group, but as group. But I explained that this group has a very non-trivial product on that. So my question is that, is it possible to recover the product from the derived categorical level? That's all for me, sorry.
So I think this is his last question.